So this is the second session on rigid body kinematics. Okay. So and this is in continuation of the first video on rigid body kinematics. So this we take up the expression for calculation of angular velocity of m of rigid body m in plane rotation with respect to some given frame f. Plane rotation has been fully discussed in the first video on rigid body kinematics. You can check it from there. Okay. So I write down what we will discuss in this second video. So m undergoes plane motion with respect to some frame f. Again, when I say plane motion, I mean plane rotation. Okay. So m undergoes plane rotation. M undergoes plane rotation with respect to f. Okay. Let omega be the angular velocity of m with respect to f at time t. Omega is the angular velocity of m with respect to f at time t. Let omega be the angular velocity of m with respect to f at time t. Alright. So now omega can be expressed in two different ways. Omega can expression, there are two different expressions for omega. Now what are the two expressions? First expression is this. Omega is equal to d theta by dt into E3 hat. And second, E3 hat I just said. Second, omega is equal to as this, I will just remove this E3 hat. Okay. So first, omega is equal to d theta by dt. So this is just the expression for omega in which I have removed the vector sign. We are just expression the scalar component of vector omega. All right, magnitude into unit vector. So this gives the expression. Okay, scalar expression. Okay, and second, omega is equal to relative normal speed by separation. Relative normal speed by separation. So these are the two different expressions for omega. We'll discuss both of them here. Okay, fine. So I'll take up the first definition now. So I'll draw the first diagram. I'll draw. Okay. This is the frame F. Okay. This is the frame from where we are observing a body M. M is the rigid body in plane rotation with respect to F. Suppose for the sake of argument, I take the sense of omega to be anti-clockwise. Okay. So P1 and P2, they are the two locations of M. Two locations of M meaning either its real location or imaginary location. They are either the real location or imaginary location of M. Real location, what is real location, what is imaginary location? You can go to the 7th video on relative velocity. There you will get all of it. Okay. So these are the two locations of M, two real or imaginary locations of M. Simply, I say that when P1 and P2 are two locations of M, which we mean that these are two locations which are fixed with respect to M. Okay, they are at rest as seen from M. That is what is meant by real and imaginary location of M. Okay. So we also impose the condition that P1 and P2 are in the same base plane. R is the distance between P1 and P2, which we will call the separation. Suppose the velocity of P1 with respect to F is this one, V1F. And suppose velocity of P2 with respect to F is this, V2F. This diagram will draw here. Okay, it has become slightly close. You can draw it here. You draw it here. Okay. So I'll draw it here. So this is the frame F. Okay. This is the rigid body M. Plane motion with respect to F. Suppose I take the sense of omega of M with respect to F to be anti-clockwise, just for the sake of explanation. P1 and P2 are two locations of M in the same base plane. R is the distance from P1 to P2. Velocity of P1 is V1F with respect to F at time t. Angle is theta 1. Velocity of P2 is V2F with respect to F at time t. V2F makes an angle of theta 2 with this line. Okay. Unit vector from P1 to P2 is E1 hat. Unit vector normal to E1 in base plane is E2 hat. Normal to E1. And omega, as we discussed in the first video on rigid body kinematics, since omega is anti-clockwise, its direction is normally outward. Okay. As I discussed in the first video on rigid body kinematics. So, this expression we use first. What we'll do, we'll derive the second expression. Then I'll derive the first expression. Okay. First I'll derive the second expression for omega. Omega is the relative normal speed by separation. Now, first of all, the vector from P1 to P2 is vector r. Where r is a vector from P1 to P2, its magnitude is equal to r. And its direction is along E1 hat. Okay. So, I'll derive the second definition of omega first. What is that second definition? Omega is equal to relative normal speed by separation. Omega is just equal to relative normal speed by separation. Omega is just equal to relative normal speed by what? Separation. Now, first of all, what is the normal speed of P2? Component of V2F normal to this line, that is the normal speed of P2. That is just V2F sin theta 2. Normal speed of P2 is V2F sin theta 2. What is the normal speed of P1? Component of V1F normal to line P1 P2. That is V1F sin theta 1. That is the normal speed of P1. Normal speed of P1 is V1F sin theta 1. Alright. This is the normal speed of P1, V1F sin theta 1. And this is the normal speed of V2, P2, V2F sin theta 2. Now, we are deriving the second expression for omega. Omega is equal to relative normal speed by separation. Okay. So see, and vector r is the vector from P1 to P2. So from vector theory, vector r can be written as magnitude of r into unit vector along direction of E1. Along vector r, that is just E1 hat. Vector r will be written as r times E1 hat. That is vector r. So vector r is equal to r times what? E1 hat. Okay, fine. Now, in the 13th video on relative velocity, I defined what is meant by relative velocity between 2 points in a given frame F. See, it is this much. dr by dt in frame F, that is the relative velocity of P2 with respect to P1 in frame F. That is just equal to V2F minus V1F. This I defined in the 13th video on relative velocity. You can go and check it there. So dr by dt in frame F is equal to V2F minus V1F. This quantity is the relative velocity of P2 with respect to P1 in frame F. Now, as I discussed in the 10th video on relative velocity, 10th video on relative velocity I discussed. In that I told you that for any vector A, 13th video on relative velocity. There I told you that for any vector A, time derivative of vector A as seen from frame F is equal to time derivative of vector A as seen from frame M plus vector omega cross vector A. This I told you for any vector A. And instead of vector A, we take vector R. This equation is valid for any vector A. So instead of vector A, we take up vector R. So we say that dr by dt in frame F is equal to dr by dt in frame M for plus omega cross R. Okay, fine. Now, this P1 and P2 are two locations fixed in M. Real imaginary locations of M. They are fixed with respect to M. So P1 and P2 are permanently at rest as seen from M. So our vector R joins is a vector from P1 to P2. Since P1 and P2 are fixed with respect to M, now this vector R is also fixed with respect to M. So as seen from M, R is a constant vector. So derivative of R as seen from M will be a zero quantity. This term will go away. So dr by dt in frame M is a zero vector. This term goes away. Fine. Now I'll wrap it here, okay? So this term goes away. Then what do we get? dr by dt in frame f is equal to omega cross r. Now what is dr by dt in frame f as I discussed just now? v2f minus v1f is equal to omega cross r. So this equation is, what does it tell us? Given a rigid body M, P1 and P2 are two material points of M. Okay. Then velocities of P2 and P1 with respect to F are related to each other by this formula. This is called the velocity equation of a rotating rigid body, which will take up in the second session on the second chapter on rigid body kinematics, which will come in the next few sessions. Okay. This I will state it just now. So now what we do now? We express V1f, V2f, omega and r in terms of E1, E2 unit vectors and substitute in this formula. And then we get the second expression for omega. Okay. So first of all, how do you write V2f? Vector V2f is equal to V2f cos theta to E1 hat. Resolution of vector into its components. V2f cos theta 2 into what? E1 hat plus V2f sin theta 2 into E2 hat. This V2f. Now how do you write V1f? V1f is equal to V1f cos theta 1 into E1 hat plus V1f sin theta 1 into what? E2 hat. Okay. Now how do you write the vector omega? Vector omega is equal to magnitude of omega into unit vector along omega. Now in this case, omega is an anti-clockwise sense. Its direction is normally outward from right hand thumb rule. So direction of omega is along outward unit vector normal to base plane. It is along direction of E1 cross E2. So direction of omega is same as that along of the vector E1 hat cross E2 hat. So omega into E1 hat cross what? E2 hat is vector omega. Now what we do? We substitute what about vector r? Vector r is simply r times E1 hat. Alright, fine. Clear? Fine. Now what I do, I rub this one, okay? I'll rub this one. I'll rub it here, okay? So we substitute all these quantities in this expression. So V2f is equal to what? V2f cos theta 2 into what? E1 hat plus V2f sin theta 2 into what? E2 hat is equal to this and substitute that side. This time I shift it to right side. V1f will substitute here. V1f cos theta 1 into E1 hat plus V1f sin theta 1 into E2 hat plus omega cross r. Omega into E1 hat cross E2 hat cross r E1 hat. Alright. Now what I do, this has simplified by the product rule. So this I write as V1f cos theta 1 E1 hat V1f sin theta 1 E2 hat plus this I replace at minus omega r E1 hat cross E1 hat cross E2 hat. A cross B is minus of B cross A from that rule. So this I write as V1f cos theta 1 into E1 hat plus V1f sin theta 1 into E2 hat minus omega r E A cross C, B into C dot A, B into C dot A into E2 hat dot E1 hat minus C into A cross B into C dot A minus C into A dot B, E2 hat dot E2 hat. Alright. So now rub this one, okay? So now this term goes away because E1 and E2 are mutually perpendicular unit vectors and dot product of two perpendicular vectors is 0. This term goes away. E2 dot E2 hat becomes 1. Dot product of unit vector which itself is 1 and minus becomes plus. So we get V2f cos theta 2 E1 hat plus V2f sin theta 2 E2 hat is equal to V1f cos theta 1 into E1 hat plus V1f sin theta 1 into what? E2 hat. And this term this minus 1 becomes plus omega r into simply this becomes a cross b into c dot a, b into minus c into a dot b. This is E2. By mistake it was written as E1. This is E2. Okay. Plus omega r, this becomes 1. A cross b into c dot a minus c into a dot b. C into a dot b. E1 dot E1. So this is E1 dot E1. Sorry. Okay. Fine. So E1 dot E1 becomes 1. And E2 dot E1 becomes 0. Minus becomes plus omega r into E2 hat. Alright. So right side I take this to E2 common. So this is just equal to V1f cos theta 1 into E1 hat plus V1f sin theta 1 plus omega r into E2 hat. Alright. So this equation is equal to this equation. So from this equation we equate the respective components of E1 and E2 on both sides. If we equate the component of E2 first, E2. On the left side coefficient of E2 is what? V2f sin theta 2 is same as V1f sin theta 1 plus omega r. So omega becomes V2f sin theta 2 minus V1f sin theta 1 by r. So this quantity, this is the angular velocity of m with respect to f. This is the relative normal speed between P1 and P2 and r is the separation between P1 and P2. So omega will be equal to V2f sin theta 2 minus V1f sin theta 1 by r. So this omega is this. So this quantity is the relative normal speed of P1 and P2. Normal speed, relative normal speed of P1 and P2. That is the relative velocity between of normal velocity of P2 with respect to P1. Velocity of P2, normal velocity of P2 with respect to P1 and P2 is what? This direction, V2f sin theta 2. Normal velocity of P1 with respect of P1 is what? Normal to line P1 P2, V1f sin theta 1. Difference we take, this is relative normal speed. So omega is equal to relative normal speed by r. R is the separation between P1 and P2. Relative normal speed by separation. So omega is just the relative normal speed by separation. This is the first proof of omega. Fine. I'll grab this one. So this is the definition of omega in plane motion. Relative normal speed by separation. Relative normal speed by separation. So omega is just equal to relative normal speed by separation, that is omega. Now in this equation we equated the coefficient of E2 on both sides. What if we equate the coefficient of E1 on both sides? On the left side of E1 equation, coefficient of E1 hat is what? This. So V2f cos theta 2 and coefficient of E1 hat is this. V1f cos theta 1. What does this say? This is just the criteria of rigid body rigidity of constraint, rigidity constraint. See, P1, P2 are two material points of M or two locations of M. So they are fixed with respect to M, rigid body M. So distance between P1 and P2 is constant. So now we know that whenever distance between two moving points P1 and P2 is constant, then component of velocity of P1 and P2 along line joining them must always be equal. This is just that equation. This we discussed in the second video on relative velocity. In the first 5 videos on relative velocity, you will get all this thing there. is just the rigidity constant, mathematical formulation or statement of the rigidity constant. Whenever distance between two moving points P1 and P2 is constant, then the component of velocities of P1 and P2 along line joining them are always equal. So this is just that familiar rigidity constant. Okay. So second definition of omega has been discussed. Rigidity constant also has been discussed. This we have discussed already in the relative velocity itself. So second definition of omega I have discussed. Now what about the first definition of omega? First definition of omega is this: omega is equal to d theta by dt. Where what is theta? Theta is the instantaneous angle between two lines. One line is fixed in f, other line is fixed in m, and both the lines lie in the same base plane. So theta is the instantaneous angle. Theta is the instantaneous angle between two lines. Instantaneous angle between two lines. One line fixed in f. One line fixed in f. Another line fixed in m. And both lines lie in the same base plane. Both lines lie in the same base plane. Both lines lie in same base plane. Okay, this is the second definition of omega. First definition of omega, which I proved. First I proved the second definition, that was more lengthy, so that I proved first, and the first definition of omega I just stated. Okay. So omega is the instantaneous angle between two lines, one line fixed in m, other line fixed in f, and both the lines lying in the same base plane. That instantaneous angle, instantaneous rate of change of that angle, that is the angular velocity of m with respect to f at time t. Alright, fine. This also I have fully discussed. Now one more thing I will say in this second chapter on rigid body kinematics, one more thing I will say. That is simply this one. One more thing which I will say is this. See, this is f, okay, fine, frame f. Suppose P1 and P2 are two moving points. P1 and P2 are two moving points, okay, with respect to f. P1 and P2 at certain instant, separation between P1 and P2 is r. R is the separation between P1 and P2 at certain instant t. Now suppose P1 and P2, they always move in the same plane. They are confined to move in the same plane as seen from f. But distance between P1 and P2 is not constant. R is not constant. There also suppose P1 and P2 move in such a way that orientation of this line with respect to f changes. Suppose that at certain instant t, this at separation at certain instant t, velocity of P1 is v1f. It makes an angle of theta 1 with this line. And velocity of P2 is v2f. It makes an angle of theta 2 with this line. Okay, fine. But r is not constant. R changes. Only one thing we have restriction we are applying. What is that restriction? P1 and P2 are always confined to move in the same plane as seen from f. But separation need not be constant. Then in this also orientation of line P1 and P2 as seen from f changes. So there also, if we want to find the angular velocity of this line P1 and P2, we can use the definition of second proof which I just now stated. There also we can say this: omega is the angular speed of line P1 P2 with respect to f. Angular speed of line P1 P2 with respect to f. Angular speed of line P1 P2 with respect to f at time t, that is just equal to v2f sin theta 2 minus v1f sin theta 1 by r, where r is the separation between these 2 points at time t. Simply what I am saying is this, that if P1 and P2 are confined to move in the same plane as seen from F, but separation between P1 and P2 is not constant, it changes with time. There also, angular speed of this line with respect to time, angular speed of this line with respect to F at time t can be found by using this formula. This formula we should derive for the case of rigid body, but this is not a rigid body. P1 and P2 do not constitute a rigid body. But here also that formula can be used. Okay, and this will give us the angular speed of this line at a certain instant t, where r is the separation between these 2 points at that instant t. There also we can use this formula. Fine. Only one thing which we cannot use in this case. What is that one? Since P1 and P2 are not, the separation between P1 and P2 is not constant. R changes with time. Therefore, in this case, we cannot say that component of velocities of P1 and P2 along this line, along line joining them, they are equal. That we cannot say. In this case, we cannot say this one. V1F cos theta 1 is not equal to V2F cos theta 2. This we cannot say. Because this is valid only when the separation between these 2 points is constant. But in this case, the separation changes with time. So this we cannot say. But this we can say here also. Only one restriction is there. What is that? This line is always confined to rotate in the same plane as seen from F. That is, P1 and P2 always confined to move in the same plane as seen from F. Then this formula can be used to find the angular velocity of this line at time t, even though separation between these 2 points is not constant. Okay, so this we cannot, in this case when separation changes, this is not true, but this is also going to be true. Only one restriction is there, that these 2 points are always confined to move in the same plane as seen from frame F. There also we can use this formula. Alright, fine. So this I have told you. Okay, so this is the second session on rigid body kinematics. So this I have fully explained here. Okay. So in the third session on rigid body kinematics, I'll take up the chapter problems of this chapter. Okay. Then we proceed to the next chapter, next topics on rigid body kinematics. So now we close it here. Fine.